it seems like only yesterday that a stranger came to town. They tell me he's a stranger young. Been shot around.
Hello, once again, this is Electronic Wizard coming at you. Unlike my last video, this is going to be an example of a series circuit. Remember, the last circuit that I did was a parallel circuit. Here it is, and I went through the math, talked a little bit about it. And when you look at a circuit like this, or like this is going to be an example of a series LR circuit. A couple of questions should come to one's mind when you look at circuits like this, whether it's inductors or capacitors or anything. Ask yourself, what do the components in the circuit have in common? In this particular case, what this circuit has in common, these components in this circuit, is current flow. So current flow is not going to be used to analyze deeper the aspects of this circuit. You would use what's different about these components, and that's the voltage drop. Here the voltage drop was similar or identical. So, but in this case, because the current is the same throughout, then you would use the voltage drops. And the second thing you should keep in mind is Pythagorean theorem and the Eli VI span. So ask yourself, what is in common with these components? In this case, it's the current flow. What's different? The voltage drops and the impedances and Eli VI span. And also one other thing, when you look at some circuit like this, note that it doesn't really do anything. It's just sitting there. But this could represent a load to another circuit or part of a bigger circuit. Or this could have a load attached to it. So that's why it's important to analyze this stuff, even though the circuit in and of itself does absolutely nothing. So going over here to the left-hand side of the screen, you have the inductive reactance for the inductor, 2 pi FL. You plug in the values, get 314 ohms. Then there's because the impedances are different and the voltages are different, that affords you the opportunity to use Pythagorean theorem. You plug in the constituent values, in this particular case the impedances, to find the total impedance. You can also do the same thing to find the total voltage, but we already know what the voltage is. But nonetheless, they do that over here. It's a form of a quick check. If you figure out and find the voltage drop of the inductor and you find the voltage drop of the resistor, you throw it into Pythagorean, and then you get your, well, in this case 4.999 volts, which is very close to 5 volts. But going back over here now, once you find the total impedance, yes, now why find the total impedance? Because now you can use Ohm's law. And now that you're at that point, everything becomes sort of academic. You take the total voltage, divide it into the total impedance, and you get the total current flow. And once you know the total current flow through the circuit, then you can find the individual voltage drops by multiplying it by the individual impedances. In this particular case, the voltage drop across the inductor is equal to the inductive reactance that they found up here, 314 or so ohms. You multiply that by the total current, 4.77 milliamps RMS, and you get the voltage drops, and then you can use the voltage drops to check to see if you've done the math right. And then they've got this vector diagram. And then they go along, and then they find the angle. Again, it's all important when you're considering this in combination with other circuits. In and of itself, admittedly, it's really academic. So, once again, because they're very minimal on this diagram, I came up with my own diagram and I made a slight modification to it. And the modification to it is to associate this with a series circuit. So when you look at a series circuit, whether it's an inductor or a capacitor, one resistor, two resistors, whatever it is, after having committed, one should commit to memory either this mnemonic or some other mnemonic. This is the one I learned from, and this is the one I've used, and called Eli the Iceman, as I stated in my previous video. Now, since this is a series circuit, you could use the straight-on Eli the Iceman for a series circuit only. E represents the voltage, in this case 5 volts RMS. I represents the current flow, which was found previously. Let's see if I can. Current flow. Here is the current flow, 4.77 milliamps. And L represents an inductor. C represents a capacitor. E is before I, which means that the voltage leads the current. It doesn't really say in this mnemonic, you're just supposed to know this, that when they say that E leads or is before I in an inductor, they mean by 90 degrees. So the voltage leads the current by 90 degrees. So when you jump way over to here to the other side of this diagram, as you can see, the dotted red line is a series circuit only inductor current. This is the inductor current through that inductor, through this inductor. So the black voltage here represents this 5 volts RMS 500 hertz. So this would be one cycle of 500 hertz. It's being pumped out of this signal generator, this voltage generator, at 500 times a second. It has no phase, 0 degrees, so you're starting out right here. And all of a sudden, you come along, and 90 degrees later, which is in a blink of an eye, in a few microseconds, then all of a sudden now, the current through the inductor starts building up because it lags by 90 degrees. According to the mnemonic way over here, voltage leads the current, or the current lags the voltage. Okay, but the current is at a 90-degree deficit when the voltage is starting out. So the voltage is leading the current in this kind of circuit, whereas just the opposite in this type of circuit. And this, when it's in parallel, the blue line represents the current, and the blue is already 90 degrees above the voltage, or past the voltage. It has a 90-degree advantage. But here, it's at a 90 degrees deficit. So that's what this graph is showing. And so that's one of the main differences between a circuit like this that's with an RL in parallel as opposed to an RL in series. So 3 things to keep in mind when you look at something like this. Of course, number one, the most obvious thing is this circuit does nothing. Keep that in mind when you see circuits like this on the internet or in books. These circuits in and of themselves are just for experimental purposes, or for just to rationalize and determine, the various constituent parts in a circuit like this. But circuits in and of themselves, unless they're a load, this could represent a motor, this could represent some type of transducer, this could represent a solenoid switch, this could represent a lot of different things. The same is true with this parallel circuit. But in and of themselves, they do nothing. So that's one thing you should keep in mind. The other thing one should keep in mind is what do these components have that are in common? In this particular case, they have current flow in common. The same current that's flowing through here is the same current that's flowing through here. What they have that's not in common are obviously their inductance, or the resistance, and the voltage drop across each one. Unlike this one, where the voltage is the same and the current is different, here you have the current the same and the voltage is different. So that's a little bit about, this is sort of an exercise and the equivalent math for a RL series circuit. Thanks for listening.
Look around.